Welcome back to The Explainer, everyone. Today, we're diving into something absolutely wild in the world of AI. You know when you're messing around with ChatGPT or checking out the outputs from open-weight giants like Llama? Well, we're going to look under the hood at the sheer logistical nightmare of training those massive models. They have fundamentally outgrown standard hardware, making training them a complete computational puzzle. But today, we're going to decode exactly how engineers solve it with some incredible matrix math and systems engineering.
Okay, let's dive right into this. 355. That is how many years it would take to train the original GPT-3 model, which honestly is kind of modest by today's standards, on a single high-end V100 GPU. Just let that sink in. We're talking centuries. The time constraint is literally impossible. So to compress all those centuries of training down into just a few weeks, engineers had to network thousands of GPUs together. But to do that without bottlenecking the whole system, they had to completely rethink how data and math flow between computer chips.
So here's our roadmap for today. We're going to hit the giant model problem, the limits of standard parallelism, exactly how tensor parallelism works, splitting transformers, the dreaded all-reduce tax, and finally, when to actually use TP.
All right, Section 1, the giant model problem. Let's talk about breaking that memory wall.
Look, the models dominating the AI landscape right now, stuff like the Megatron Turing NLG or the latest Llama 3 herd, they are packing hundreds of billions of parameters. At that scale, the model physically outgrows the memory capacity of even the absolute best single GPU. Actually, scratch that. It outgrows entire multi-GPU servers. You can't just load the model up and hit train. It creates this totally unbreakable memory and compute wall. We literally have no choice but to distribute the model across multiple chips.
Moving on to Section 2, the limits of standard parallelism. Let's see why the old tricks just don't cut it anymore. Traditionally, we'd rely on a couple of main go-tos. First up is data parallelism. That's where you copy the whole model across multiple GPUs and feed each replica different data. But, as we just established, our giant models don't fit on one GPU, so that's out. Then there's pipeline parallelism, which slices the model into sequential stages. Layers 1 through 10 go to GPU A, layers 11 through 20 to GPU B, and that works great for really deep models. But here is where the structural limits start to crack. What happens if a single layer, like one of those massive self-attention blocks inside a transformer, is so colossal that it alone blows past the memory of a single GPU? Boom, both data and pipeline parallelism completely break down.
Which brings us to Section 3, how tensor parallelism works, or as I like to call it, divide and conquer.
So, here is the ultimate intra-layer fix to our scaling wall, tensor parallelism, or just TP for short. Instead of putting different layers on different GPUs, we take one single layer, slice its internal mathematical matrices into pieces, and assign those chunks to multiple GPUs to work on at the exact same time. Think of an assembly line building a car. Pipeline parallelism is like passing the car down the line. You add the doors, then pass it to the next person for the wheels. But tensor parallelism, it's totally different. It's like a crew of mechanics surrounding the car and building the exact same engine block together, simultaneously. It is a true divide-and-conquer approach for just a single layer of a neural network.
Section 4, splitting transformers. Let's take a peek inside Megatron LM.
And this brilliantly illustrates what happens when we look directly under the hood of a transformer architecture. A standard transformer layer has two main heavy-lifting parts: the multi-layer perceptron, or MLP, and the self-attention block. Now, the Megatron LM design shows us that to actually distribute that compute load efficiently, we have to slice these matrices up in a very specific way. You'll see some sliced vertically into columns, and others sliced horizontally into rows.
Let's walk through the actual math flow for that multi-layer perceptron. Step 1, we take the first weight matrix, matrix A, and split it up by its columns across our GPUs. Why columns? Well, by splitting matrix A by columns, each GPU can calculate its chunk of the GLU nonlinear activation function completely on its own. They don't need to pause and sync up with each other, they just crunch the math. Finally, for step 3, we take the second weight matrix, matrix B, and split it by its rows. This very specific combo, column split, compute independently, row split, is what allows the parallel math to flow smoothly.
And guess what? The self-attention blocks use the exact same logic. You take that inherently parallel multi-head attention mechanism and distribute it out. You column split the key, query, and value matrices across your GPUs. They all do their attention calculations simultaneously, and then you row split the final output linear layer. This precise choreography is exactly what lets the GPUs chew through that multi-head attention math in parallel with minimal interruptions. But notice I said minimal interruptions, because yeah, there is a catch.
Section 5. The all-reduced tax. Ah yes, the communication overhead.
So, because we sliced all these matrices apart and handed them out, we eventually have to stitch the separated math back into one cohesive result before we can move on to the next block. We do this through a mandatory synchronization step known as an all-reduce operation. It literally gathers up the partial answers from every single GPU, tallies up the total sum, and broadcasts that final answer back out to everyone. Simple enough, right?
But this brings us to a critical bottleneck, and I really want you to consider this question. What happens when GPUs talk too much? Seriously, if they spend all their time just communicating the results of their math over the network, when are they actually doing the math?
Now what's really interesting about this is what happens as you scale up. Say you increase your tensor parallel size, spreading a layer across 8 GPUs instead of 4. You start introducing what researchers call TP bubbles. Basically, these are dead zones where the GPUs are just waiting for data to travel over the network during that all-reduce step. The research shows this communication can eat up to 27.5% of the total training time. That is a brutal tax on your system's efficiency. You're paying a massive premium in time just for the chips to chat with each other.
All right, final section. Section 6, when to use TP. Let's talk physical hardware boundaries.
Given this massive tax, how do we actually use this practically without totally tanking our efficiency? The secret lies in respecting those physical hardware boundaries. Inside a single modern AI server, or a node, your GPUs are wired together with ultra-fast links called NVLink. We are talking mind-boggling speeds, up to 1,800 gigabytes per second. But to connect different physical servers together across a whole data center, you use InfiniBand, which is significantly slower. Because tensor parallelism demands constant communication, if you try stretching a TP group across that slower InfiniBand network between servers, the all-reduced tax is going to absolutely crush your performance.
So the crucial point here is that we have to mix our strategies to create what is known as 3D parallelism. This is the exact playbook used to train record-breaking models like that 530 billion parameter Megatron Turing NLJ. First off, you restrict tensor parallelism strictly to a single server node, exploiting that insane NVLink bandwidth to pay the all-reduced tax in a flash. Then, since your model is still way too big, you use pipeline parallelism to chunk the model across different physical nodes, because that requires far less network chatter. And finally, if you've got even more hardware available, you wrap the whole shebang in data parallelism to chew through massive datasets faster. It's an elegant, multi-layered symphony of systems engineering.
We've seen how slicing up a transformer's matrices lets us completely shatter that memory wall, provided our networks are fast enough to handle the gossip, of course. But this leaves us with a final, pretty provocative thought. As our large language models inevitably scale out of the hundreds of billions and into the trillions of parameters, the math is going to demand even wider parallelism. So how will our physical network interconnects evolve to satisfy this absolutely insatiable demand for data transfer? That is the bleeding edge of AI infrastructure, and for sure a topic we'll be keeping a close eye on. Thank you so much for joining me on this deep dive into tensor parallelism. Keep learning, and I'll catch you on the next explainer.